Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about the idea of activation energy as well as we're going to talk about catalysts. So let's get into this video. So the first thing we're going to talk about is the idea of activation energy. And the best way to think about this is by looking at these reaction coordinate diagrams. So let's look at the pieces of this reaction coordinate diagram. You've got the y-axis, which is labeled as energy, as well as on the x-axis, it's going to be labeled reaction coordinate. And this is kind of like time, but it's not really time. It's just as this particle goes through the reaction process, you're going to see where throughout the process the particle is at in terms of its energy. So if we've got some compound, some reactant, and it's got some initial energy value, and then as you go through the reaction process, you're going to start to build some new bonds and you're going to break some old bonds. So you're going to get at this peak energy value, and this peak energy value is the activation energy barrier that you need to overcome. At the top of this peak here, this is called the transition state. And this is where you've got half bonds being broken and half bonds being formed, and it's the highest energy input that you're going to have to overcome. Then as you start to go down the hill, you're going to get lower and lower energy as you start to form your new bond and those bonds are finally broken. So to go from your reactant energy value to the tippy top of the transition state, this is going to be your activation energy. And whatever energy value you started with and whatever you ended with, this is your change in energy. So in this case, it looks like we have an exothermic reaction because we've got some reactant value and the overall energy is lower than what you started with. So that's our change in energy. So when we're talking about activation energy in terms of speed, we're going to have particles going at all different speeds. And remember, the particles need to slam into each other in order for a reaction to occur. They need to slam into each other with enough energy, the activation energy, in order for the product to be formed. So the bigger the activation energy, the larger the barrier you need to overcome in order for the reaction to take place. Therefore, the slower it's going to go. Higher activation energy, lower rate. If the activation energy is much smaller, then it's a smaller barrier you need to overcome for the reaction to take place. Therefore, lower activation energy, faster reaction. The other thing we're going to talk about this video is going to be the idea of a catalyst. So a catalyst is something that's going to lower the activation energy by creating an environment that's going to be beneficial for that reaction to take place. Most of the time it's going to be orienting particles so that whatever sides of the particles need to interact with each other are facing towards each other, as well as it might stabilize some electron cloud regions or donate some positive charge or negative charge depending on what kind of interactions you're going to have with the catalyst. So there are going to be three major kinds of catalyst. The first one we've got is homogeneous catalyst. This is going to be a catalyst that's in the same phase. So if we have something like hydrogen peroxide, H2O2, and this is going to degrade to form water and release oxygen gas, the bubbles, so if you get a cut and you can see the bubbling on your skin when you pour that compound on there, it's releasing oxygen gas. Well, we can use a catalyst to cause this to go faster. And by doing that, we're going to lower the activation energy. So if we put in some halogen like hydrochloric acid or hydroiodic acid, that iodide ion is going to act as a catalyst, allowing that oxygen gas to be released even quicker. So by lowering the activation energy, you're increasing the speed. We also have heterogeneous catalysts. This could be something like a metal plate, where in your vehicle, you've got a catalytic converter, which is some platinum catalyst, and it's there to help scrub out the nitrogen-containing contaminants that would be coming out of your exhaust pipe, so that you're only releasing carbon dioxide and water vapor out into the atmosphere. The other times where you could be using a metal heterogeneous catalyst could be the hydrogenation of an oil, where you're using some metal catalyst and you're bubbling hydrogen gas over a compound that has double bonds. That's an unsaturated fat. So if you have some vegetable oil or olive oil, it's very liquid-like, and then you want to hydrogenate it to maybe get some hydrogenated oil or those little teeny butter cups, you can bubble hydrogen over there, and it's going to break that double bond, causing hydrogens to stick on those new two positions. So you're going to saturate this fat with hydrogens, a saturated fat. You could also do this with ethene or ethane, but what the heterogeneous catalyst or the metal is doing is it's helping to orient the particles in order for them to interact with each other as well as stabilize charge. The third category, which is pretty much the most amazing catalyst that we have on Earth, are these enzymes. Enzymes are the biological catalyst. And biochemists have a little bit different words that they like to use. So we have an enzyme, which is a protein, a string of amino acids, and then this protein folds into a little machine that might do something. So if we have something like ATP synthase, this is an enzyme that is going to synthesize ATP. So it's acting like a clamp. You're going to have an active site, which is a little pocket that perfectly fits the compounds that need to bind them. Biochemists call these substrates. So adenine diphosphate, or ADP, is going to bind to the active site. Inorganic phosphate is going to bind to the active site. And then this enzyme catalyst little micro machine is going to clamp them together, creating an environment able to do so by lowering the activation energy. And then when it opens up again, ATP is going to come out. And this machine's job is to just clamp ADP and inorganic phosphate and make ATP over and over by the use of a turbine. So the way that it's doing this is its amino acid side chains are helping to stabilize that compound within the active site. So enzymes are very specific to the substrate that they bind. It's like a lock and key method, to where you've got only a certain key will open that lock, well, only a certain active site will fit those certain substrates. So it's very specific. So there it is, you guys. There's the video on activation energy and catalyst. If you enjoyed this video, don't subscribe this time. Smash the thumbs down button, and we'll see you in the next video.